So good morning all. In this video you will see the basic concepts of Smith chart. Smith chart is basically used to find out the transmission line characteristics like input impedance, reflection coefficient and VSWR. So you can read it out. The characteristics of a transmission line are Z in tau S. These are determined by the parameters R, L, C, G, which are the line parameters of the transmission line. One way to find out Z in tau S is using equation, which is a tedious process. So Smith chart is a graphical technique used to find out Z in tau S, etc., especially when the load impedance is complex. Okay, when the load impedance is complex, Smith chart is very helpful in finding Z in tau S, etc. Okay. Now this is a typical Smith chart, and here you can see some sort of circles. There are two different types of circles. One is you can see two different types of circles. Okay, one is, see, this one is drawn in like this. Okay, you can see this is known as resistance circle. Other type is, you can see here, here, this one starting from like this form you can see here, right? Both sides you are having, like here also, both side you can see lines like this. These are known as, this one also, like this, you can see here. These are known as reactance circle. So there are two types of circles, resistance circles and reactance circle, and Smith chart is a combination of resistance and reactance circle. So how these resistance and reactance circles are formed, we will see in the coming slide. So here you can see, so here you can see development of Smith chart. Smith chart is constructed with a circle of unit radius. Okay. Now development of Smith chart is based on the relation tau is equal to ZL minus Z0 by ZL plus Z0, which we already derived in 4th module, where ZL is a load impedance and Z0 is a characteristic impedance. Now we know that reflection coefficient has a real part and an imaginary part. So I am writing tau as tau r plus j tau I, where the first term represents a real part and the second term represents a imaginary part. So it can be represented in the polar form as modulus of tau angle theta. Now what I am going to do is I am going to divide all these terms by Z0. So I will get ZL by Z0 minus 1 by ZL plus ZL by Z0 plus 1. That is done here. ZL by Z0 minus 1 divided by ZL by Z0 plus 1. Here the term capital ZL by Z0 is known as normalized load impedance, which is represented as small zl. So I can write tau is equal to small zl minus 1 by small zl plus 1, where small zl is equal to capital ZL by Z0 is your normalized load impedance. So why you are normalizing the load impedance, it will be clear when you do a problem. Actually, by normalizing the value of the load impedance, what we are trying to do is we are trying to minimize the value of load impedance. So what happens is, if you are not normalizing the load impedance, if the load impedance value is very large, it will be quite difficult to plot the load impedance on your Smith chart. So what we are doing is, ideally we will minimize the value of this ZL by dividing it with Z0 before plotting the point on the Smith chart. It will be clear when you do a problem. Now I told you that Smith chart is of more importance when you are using a load impedance which is complex. So small ZL is represented as a complex load where the real part R represents a resistance term and the imaginary part represents a reactance term. That is what I said earlier, that the Smith chart is a combination of resistance and reactance circle. Now instead of tau, I am writing tau R plus j tau y, that is equal to small ZL minus 1 by ZL plus 1. Then I am cross multiplying, then rearranging the terms. Finally, I will get small ZL. My normalized load impedance is equal to 1 plus tau R plus j tau y by 1 minus tau R minus j tau I. In the next step, what I am doing is, I am simply multiplying the numerator and denominator by 1 minus tau R plus j tau y. Multiplying, rearranging. Finally, I will get small ZL is equal to this equation 1. Okay. Similarly, I know what is ZL in terms of R and X. R plus jx, where R is your resistance value and X is a reactance value. Then I can compare equation 1 and equation 2. From that I will get R and X. That is my equation 3 and equation 4. In the next step, what I am going to do is, I am rearranging, I am cross multiplying equation 3, rearranging the terms, and finally I will get equation 5 as tau R minus R by 1 plus R the whole square plus tau Y the whole square equal to 1 by 1 plus R the whole square. Similarly, I am cross multiplying equation 4, rearranging the terms. Finally, I will get equation 6, that is tau R minus 1 the whole square plus tau y minus 1 by x is equal to 1 by x the whole square. This tau y you can simply write like this, that is tau I minus 0 the whole square, which is equal to tau I square. So this is my equation 5 and equation 6. Now you can see this equation 5 and equation 6 are similar to x minus h the whole square plus y minus k the whole square is equal to a square, where x is equal to what? Equation 5. In equation 5, x is tau R, and equation 6, x is tau R. Same, right? Then y. In equation 5, y is tau I, 6 is tau I. Then what is h and k? Here in equation 1, h is R by R 1 plus R, and here it is 1. And k, here it is 0 and here it is 1 by x. Then a, here it is 1 by 1 plus R and here it is 1 by x. So equation 5 and equation 6 are similar to a circle with a radius a and center h comma k, where equation 5 is called resistance circle whose center is R by 1 plus R comma 0 and radius is equal to 1 by 1 plus R. And equation 6 represents a reactance circle whose center is 1 comma 1 by x and radius is 1 by x. So this is the expression for the center and radius of your resistance circle in the Smith chart, and this is that of reactance circle in the Smith chart. And this table is not necessary. Now here you can see, earlier I have shown in the Smith chart, this type of circles are known as resistance circle, which is drawn like this. Here you can see resistance circle, and similarly reactance circle. You can see here, is drawn like this, like this, like this, like this. So Smith chart is a combination of both resistance circle and reactance circle. Now there are few points that you have to keep in mind. Moving 360-degree along the circle in Smith chart is equivalent to moving lambda by 2 length in the transmission line. That is, if you make one complete circle in the clockwise direction like this, starting from this point, this is the starting point 0. Here you can see wavelength towards the generator. So you have to start from this point, move like this in the clockwise direction, come like this, and coming back to this point is equivalent to lambda by 2 distance. That is your first point. Moving 360-degree along the circle in the Smith chart is equivalent to moving lambda by 2 length in the transmission line. Second point is moving clockwise direction in Smith chart is the movement from load to generator. That is, if you are moving in this direction, that means you are moving from the load to generator. Here, clockwise, here you can see this is the starting point. Now we are moving in the clockwise direction. So here you can see the arrow written wavelength towards the generator. So if you are moving in this direction, then that means you are moving from load to the generator. If you are moving in the anti-clockwise direction like this, that means if you are moving from generator to the load. That is written here. Moving clockwise direction in Smith chart is a movement from load to generator and vice versa. Then diametrically opposite point of impedance gives the admittance. If you find out the impedance point in your Smith chart, then it is easy to find out the admittance point also. How? It will be diametrically opposite to that of the impedance. So Smith chart is also known as admittance chart or impedance chart. So these are the basic things that you have to keep in mind regarding Smith chart, and this derivation is also very important. Hope it's clear, and thank you.